Hi everyone and welcome. I'm Gavin Lon. The video you're about to view is an excerpt taken from a full approximately 5-hour and 20-minute course published on the FreeCodeCamp YouTube channel. The full course was made possible by a grant provided by Neo4j and can be viewed in its entirety at this URL. I thought the overview that I created for this course could stand alone as its own short video, where an overview comparison of the most popular database management system types is provided. I'd love to know which database management system types you have used, which ones you prefer, and why. So please let me know in the comments section. I hope you enjoy this video. Hi and welcome, I'm Gavin Lon. So, I finally got my FreeCodeCamp t-shirt. I traveled all the way from the east coast of South Africa to Amsterdam and met the founder of FreeCodeCamp, Quincy Larson, and he gave me my own FreeCodeCamp t-shirt. Really great. So the point of the trip was to meet Quincy and some of the core team members of FreeCodeCamp in person. It was about team building and solidifying relationships between co-workers. The key concept in this course is in fact relationships. Relationships between data. The relationships could be between people, between car parts, between a t-shirt and a human being. So relationships between homogeneous data or like data, for example, between human beings, or relationships between heterogeneous data or different types of data. These relationships can be very effectively represented within a graph database management system. Neo4j is a graph database management system. In this part of the course, I want to present to you a brief overview highlighting the significance of a graph database management system. Before we look at Neo4j, let's contextualize the significance of a graph database management system by looking at some of the other popular types of database management systems commonly used today. So let's look at 3 other commonly used types of database management systems before we discuss the graph database management system, and why we would want to use a graph database management system in our applications. The most well-known used database management system type is a relational database management system. Examples of relational database management systems are SQL Server, Postgres, and MySQL. In this type of database, tables represent entities. For example, a table named employee contains rows of data. Each row of data is divided into columns or fields containing employee information. For example, the name field contains the employee name. The age field contains the employee's age, etc. Another data entity could be implemented in a table named department. Each row in the department table denotes an individual department. For example, one row stores information for the human resources department and another row stores information for the finance department. These data entities or database tables within a relational database can be explicitly related to one another within the relational database management system. For example, an entity may have a one-to-one relationship with another entity. So say employees and the cars they drive. A specific employee is related to a specific car, one employee to one car. So for example, the employee entity in this case has a one-to-one relationship with the car entity. 2 database tables can have a many-to-many relationship. For example, an employee could be a member of multiple teams, and each team can contain multiple employees. So this means an employee can be a member of more than one team, and each team can have many employees. So in this scenario, the employee entity has a many-to-many relationship with the team entity. A database entity can have a one-to-many relationship with another database entity. For example, the department table has a one-to-many relationship with the employee table, meaning each department can contain one or many employees, and an employee can only be a member of one department at a given time. So this one-to-many relationship can be established within the relational database management system through an appropriate schema design. A database schema defines how data is organized within a relational database, which includes constraints such as table names, fields, data types, and the relationships between the relevant entities. So for example, the one-to-many relationship between the department table and the employee table can be implemented by including a primary key, which is a unique identifier for a row of data in the department table, and a foreign key field within the employee table, which relates to the primary key value within the department table. The main advantages of a relational database design is that it helps facilitate data integrity, so the data is not easily corrupted, as well as reduces data redundancy. Storage for repeated values are reduced. For example, if you stored department data within the employee table, you can see here the department short name field and long name field values are repeated across rows in the employee table, whereas separating the data into an employee table and a department table means these values are not repeated, resulting in saving storage space. As the data scales, this storage saving can be quite significant. A technique known as normalization is employed to design a relational database. I won't go into the details of normalization here, but please look up normalization, which is a key concept in relational database design. So the technique of normalization can increase data integrity, minimizing data corruption and also significantly reducing data redundancy, i.e. unnecessarily storing values repeatedly. The downside to relational databases is the speed of retrieving data when multiple joins or deep joins between entities are necessary. For example, if you want to retrieve analytical data that summarizes data from multiple entities, a normalized database design can cause the retrieval of such data to be a slow process. So, a way to speed up data retrieval can be to use a schemaless database management system like, for example, MongoDB. This is a document-based database management system. The fact that the database design is not bound by a schema, like with a relational database management system, can result in increased speed of data retrieval, as well as allow for better design flexibility. So you can see that each of these database management systems have their purpose and advantages. Another type of database management system may use a name-value pair storage structure, like for example Redis. This database management system is great for caching frequently retrieved data and therefore can help speed up a system. So we have briefly looked at 3 common types of database management systems. Relational database management systems like for example SQL Server or Postgres, schemaless database management systems like for example MongoDB, and name-value pair database management systems like Redis. So let's look at the significance of a graph database management system. Neo4j is a graph database management system. This type of database management system is based on the graph data structure. All of these social media platforms use graph databases: Twitter, Facebook, and Instagram. As we all know, these platforms have millions of users. A relational database management system would not be ideal as the only storage facility for such data. Because of the way the data is structured, would mean multiple joins between entities would need to be made when relevant data is retrieved, which would drastically slow down the data retrieval process, ultimately causing a poor UX, user experience, because the whole system is slowed down by these joins that need to be made between data. So note that when designing a particular system, like a social media platform, you could incorporate both a graph database management system and a relational database management system into your overall system design. This type of solution could combine the enforced data integrity inherent in relational database management systems with the complex relationships between data entities or nodes that can be facilitated using a graph database management system. For example, the master database could be a relational database where data integrity and data redundancy concerns are addressed by the inherent benefits that we have discussed regarding a relational database management system. A graph database management system that is appropriately synchronized with the relevant relational database management system can be leveraged to increase the retrieval speed of data that, for example, has complex relationships. If data that requires complex relationships was retrieved directly from the relational database management system, the joins required when retrieving the relevant data could significantly slow down the system and ultimately result in a very poor UX, user experience. So by including a graph database management system in the overall system where it sits on top of the relational database management system, as it were, and is used to speed up the retrieval of data with complex relationships, this could significantly speed up the data retrieval process, resulting in a far better UX, user experience. So this sort of system would require that the data stored in the relevant graph database management system and the relevant relational database management system be synchronized so as to ensure that the data is consistent across the two disparate database management systems. So a system like this, when designed properly, can leverage the benefits of both types of database management systems. For graph-based data structures, a database management system that focuses on the facilitation of relationships between entities or nodes is essential, and a graph database management system provides a way to store data based on the graph data structure, which is ideal for applications that consume data where entities have multiple relationships and complex relationships with one another. Think about social media platforms where you have relationships between users and posts, likes, friendships, etc., and you have millions of people using these platforms. A database management system is needed that appropriately facilitates the storage of data for a large number of different types of relationships. A graph database management system allows for relationships to be stored as data within the graph database. With a relational database management system, the emphasis is on the entities, and generally the relationships between the entities are not stored in the database, but rather general relationships are established at the design level. For example, you can see by the foreign key field value that the employee is a member of the HR department, but there are no details about the relationship itself between the relevant department and employee saved in the database. This is something you could easily do within a graph database management system. You could create a more detailed relationship. You can easily save data regarding individual relationships between entities or nodes, for example, between an employee node and a department node. So here's a whiteboard presentation that shows how the relationships between individual employees and departments could be represented within a graph database. So here we see a node that represents a department. This node is appropriately labeled department. Details related to this department node can be saved to the database as properties and related values. So this department contains a short name property with a value of HR and a long name property with a value of human resources. Here is our first employee node. This node is appropriately labeled employee. The employee node contains properties and relevant values representing the employee's name and age. Here we see our first relationship. This relationship explicitly shows that the employee, whose name is Brad Jenkins, is part of the HR department. This relationship is appropriately labeled member of. So you can see that this is a very human-readable representation of data. The fact that this employee is a member of the HR department is clear through appropriate labeling and properties. So Brad Jenkins is a member of the HR department. We are able to add properties to the relationships themselves. So the member of relationship has a join date property as well as an employee type property. You can see by this data when this employee joined the department and that this employee has a permanent role and is not, for example, a contractor. Here we have the second employee node, who has the name Jenny Lane. Jenny is also a member of the HR department. We can save relationships between employees within our graph database. So Jenny works with Brad. We can also create another works with relationship in the opposite direction where Brad works with Jenny. So you can see that we have a one department to many employees relationship, just like what was shown earlier in the relational database, but a graph database is far more flexible in terms of design when establishing relationships between data points or nodes. Not only can the entities contain associated data, but the relationships themselves can also contain data, i.e. through properties and associated values. So we could create even more complex relationships between nodes. For example, a chain of command hierarchical structure related to our employee nodes. So here's an example of this where employee James Stokes reports to another employee, Jenny Lane. This is just a simple example, and of course this hierarchical data structure could become far more complex. So this presentation was only intended to give you a basic idea of how much more flexible the design of relationships between entities can be within a graph database, and how complex relationships between entities can be easily implemented within a graph database. I want to show you a brief demonstration of using Cypher to query a graph database, and to do this, I'll firstly create a Neo4j database on my local machine. I'll use my Mac platform to demonstrate this. I'll contrast using Cypher in Neo4j with using SQL in a SQL Server database, which of course is a relational database management system. Firstly, what is Cypher? Cypher can be likened to SQL, or structured query language. Cypher is a text-based declarative language used for querying a Neo4j database. What is meant by a declarative language? A declarative language is a high-level language that describes what a computation should perform. These languages must follow strict semantic rules, must be structured in a particular way, in order to be valid and for desired results to be returned from the relevant database management system. For example, using SQL in order to bring back all employee records from the employee table, you would appropriately execute the following SQL code. This SQL statement simply returns all rows and all columns from the employee table. Using Cypher, if you wanted to return all employee data, you would use a query like this. This query would return all employee nodes and relevant relationships. Although when comparing these two query languages, they are of course semantically different, but principally they are the same in that the relevant declarative text-based code is parsed by the appropriate database management system, converted into appropriate instructions that are executed under the hood, as it were, and the relevant results are then returned from the relevant database. I'd like to demonstrate using Cypher within a Neo4j database. I'll contrast executing Cypher against the Neo4j database with executing similar queries against a similar database implemented in a SQL Server database. You don't need to follow along with this part of the course, but of course you can if you want to. So if you want to follow along, you can install Neo4j on your Mac or Windows platforms by following the instructions at this URL. I have already installed Neo4j on my Mac platform. If you want to install a free version of SQL Server, please navigate to this URL. But as discussed, this part of the course is only intended to be an overview and not a detailed explanation, so it's not necessary to follow along with this part of the course. I've created these scripts on GitHub for this part of the demonstration. So I'm going to copy this script from GitHub and run it in Neo4j to generate my Neo4j graph database. So within Neo4j Desktop, let's create a new project. I'm going to call this project Sample Project. Then let's create a new database. I'm going to name my Neo4j database Company DB. Let's give our database a password. Then let's press the Create button. And now we need to start the database, so let's press the Start button to do this. Then to execute our Cypher queries, let's click this Open button and open the appropriate window from which we can execute our Cypher queries. So the first thing we need to do is copy the code for creating our graph database. So let's navigate to this appropriate GitHub URL. Let's copy this code from GitHub and appropriately paste the code within the window that we can use to run our queries through Neo4j Desktop. Great. And let's click the Play button to create our graph database. Excellent. And we are presented with appropriate status information telling us that our graph database has been created successfully. I'm going to run this script within SQL Server to generate a similar database, the difference of course being that this database is designed as a relational database. So let's appropriately copy this SQL code from GitHub. Let's launch SQL Server Management Studio. Let's run our SQL code to create our database. I've already created a database named the Company DB Test, so I'm going to create a new database named the Company DB Test 2. Then I need to change the relevant SQL script to point to the new database that I've just created. Let's press the Play button to run the script and create our database tables and relevant data. Great. So I'm going to run a few queries so that you can get a basic understanding of the differences and similarities regarding Cypher and SQL. So let's run this query against the Neo4j database. Great, this query brings back all the employee nodes and relevant relationships. In order to retrieve all employee data from within the relevant SQL Server database, you could run a SQL query like this. And let's say we wanted to retrieve particular data about a particular employee. So you could run this Cypher code like this. Within the SQL Server database, you could run a SQL query like this. Okay, so now the next query I'd like to run is a little bit more interesting. So in both these two databases, we have expressed a hierarchical relationship between employees. In the Neo4j database, this is implemented through the report to relationship established between employees. In the SQL Server database, the same hierarchical relationship between employees is expressed, but through the use of what's known as a self-joining table. So in this case, the employee table joins to itself through the relationship between the report to ID field and the ID field, which stores each employee's ID. So in the employee table, the hierarchical relationship between employees is established through the use of the report to ID field, which stores the employee ID of the relevant employee's immediate boss, if you like. So employee Brad Jenkins is at the bottom of the hierarchy, as it were. So if you wanted to query the SQL database to get the chain of command from Brad Jenkins to the top of the hierarchy, you need to run a query like this. As you can see, this query is really difficult to understand at first glance, and recursion is used to get the desired results. A graph database is far easier to understand in terms of retrieving such tree data structures from the relevant database. So to use Cypher code to retrieve the relevant hierarchical data, starting with an employee at the bottom of the hierarchy, Brad Jenkins, you would run Cypher code like this against this particular database. Great! Okay, so I hope this part of the course has given you at least a basic understanding of a graph database management system and how you can benefit from incorporating a graph database management system into your application. Well, I hope you enjoyed this video that broadly compares the most popular database management system types available today. If you liked this video, please hit the like button and please consider subscribing. Please also ring the bell so that you'll be notified of future content. Please feel free to share this video with anyone you feel may benefit from its content. If you'd like to thank me by buying me a coffee, you can do this through my Buy Me a Coffee webpage at this URL. It will of course be greatly appreciated. I love reading your comments, so please feel free to engage with me in the comments section. I've recently joined X, formerly Twitter, so it would be great if you followed me on X. My username is @GavinLonDigital. I hope to see you soon. Thank you, and take care.